Greetings everyone! I have prepared a few more example problems for you. These are for your use in studying for the final exam. These are a little bit harder than the normal example problems that I give because they combine multiple ideas together at the same time. Today we're going to be looking at a problem that combines two-dimensional kinematics as well as gravity into one larger problem. Just in case anyone is wondering, I tend to collect rocks, starships, and coins. So you've seen a lot of the rocks and starships that I've got. Here's some coins. That's from ancient Rome. It's from about 340 AD, give or take. That is a silver dollar from 1922. And that is a coin that I got from the Department of Nuclear Physics at West Point when I gave a presentation on my research there. So they're neat. Anyway, what we're looking for is a problem combining two-dimensional kinematics and energy together. Here's the situation. We've got a hill, and we've got a ramp at the end of this hill. We've got a skier. That skier wants to land exactly 14 meters away from the end of the ramp. Here's the end of the ramp. The ramp is 9 meters tall. Skier wants to land 14 meters away, right there. The angle of the ramp is 35 degrees. At what height should the skier start at zero initial speed in order to land exactly where he wants to land? Where should he start? Where on this hill should he start? How high up should he start in order to, starting from zero velocity there, pick up some speed, lose a little bit of speed, go off the ramp at some speed, just the right speed, so that he lands exactly 14 meters away from the end of this ramp right there, and that height right there being 9 meters. Where should he start up there? Obviously, there's a lot going on in this question. And when you see a question like this, I hope that you can see that it's not really any of our individual types of questions. There's so much going on here that it has to be multiple kinds of questions all at the same time. The key is to figure out where to divide each part from each other and figure out what each part really is. We're given a lot of information over here, and we're asked for information over here. We're really being given the final state of the problem. The skier does land there. Where did the skier begin? Okay, ignore all that. The skier ends there, 14 meters away from the bottom of the ramp, from the end of the ramp. The ramp is 9 meters tall and it has an angle of that. I'm just ignoring everything else. All I'm looking at is this ramp, that height, and that distance. What kind of problem is it looking at the end of the problem? This should be a kinematics problem at the end. If I know how far away he lands, and how high up he started, and what angle the ramp was at, I'm pretty sure I can find the initial velocity there. Now, in class, we often had problems where we had an initial velocity right there and a height, and I asked you to find that distance. We had that problem about the cannon on the castle shooting at the pirate ship. I gave you the velocity of the cannonball and how high up it was on the castle walls and the angle that the cannon was firing at. And I said, okay, find how far away it lands in the water down there. Now we've got kind of the opposite. I give you how far away it lands, and you need to find the initial velocity up there. Okay, if you knew the velocity right there, let's say that that was the only other thing you knew. You knew the velocity right there. Well, let's cover up that. And let's say, okay, I know the velocity right there. When I'm 9 meters high, I know the velocity at a height of 9 meters. Where was my velocity 0? At what height was my velocity 0? If I give you, well, when I'm 9 meters above the ground, my velocity is such and such. Where was my velocity 0? What is that? Yeah, that's an energy problem, a conservation of energy problem. That's the easiest way. We don't know exactly what this hill looks like, so we have to use conservation of energy to figure out how high up the skier was when he had 0 velocity to have the exact right velocity there. So, what do? We start at the end of the problem. We start all the way over here. How fast does the skier have to go at the end of the ramp? How fast does he have to be going there in order to land 14 meters away from the bottom of the 9-meter ramp? This is a two-dimensional kinematics problem. Well, to be going that fast, where should he start? That is an energy problem. So let's try it out. So, how are we going to figure out the velocity there, given all of this stuff? Well, what do you think? I'll give you some time to think. Yeah, this is the two-dimensional kinematics kind of problem. So we do these famous equations that everyone loves. Delta x is equal to v naught xt plus 1/2 ax t squared, and delta y is v naught yt plus 1/2 ay t squared. Remember that? Remember that from a billion years ago? Well, we've got to remember that for the final. This is a cumulative class. We've got to remember all this stuff on the final. So get studying that. Okay, let's go through it. What is delta x going to be in this problem? Well, looks to me like delta x is going to be 14 meters. Our starting point is there. So we need to go right 14 meters. What is v naught x going to be? Well, I don't know. We need to figure that out. What's t going to be? Well, I don't know. We have to figure that out. What's ax going to be? Yeah, ax is 0. Ah, remember that stuff? Okay, if you don't, go back and look at that. And so this whole term doesn't matter now. Delta y, what is delta y going to be? Okay, be careful. I bet a lot of you just got something wrong. Delta y is not 9 meters. It's negative 9 meters. Delta y is negative 9 meters. He needs to go down 9 meters, not up 9 meters. He needs to go down 9 meters. If he was trying to get up there, then you'd be right, that he needs to go up 9 meters. But no, he needs to go down 9 meters. Negative 9 equals v naught y, I have no idea, times t, I have no idea, plus 1/2. What's ay? Yeah, negative 9.8 meters per second squared. The acceleration due to gravity near the surface of the Earth, times t squared. Okay, let's start thinking about what we're going to do with these v naught x's and v naught y's. How am I going to figure out what v naught x is? What's the equation for v naught x? V naught x is equal to v naught, the initial velocity, which is going to be the velocity at the end of the ramp, times the cosine of theta. Theta is 35 degrees. I can plug that into my calculator, and I get that v naught x is equal to 0.819 v naught. Okay? Same thing for v naught y. V naught y is equal to v naught sine theta, the x component of the initial velocity, the y component of the initial velocity. Plug that into your calculator with theta being 35 degrees, 0.574 v naught. You can see where the velocity is. Every vector has components, so most of the velocity is in x. I guess 81.9% of the velocity is in x and 57.4% of the velocity is in y. So you can tell that it's going to be not quite as y as it is x, so it's got to be less than 45 degrees somewhere, just based on that, but we know it's 35. Just making sure that these answers look reasonable. Well, what can we do with this? We can plug this in for v naught x and this in for v naught y. We can also make sure that we get rid of that term right there. And what do we get? For delta x, we say, okay, delta x is 14, v naught x is 0.819 v naught times t, and this thing was 0. And then for y, we have -9 is equal to v naught y, but v naught y is 0.574 v naught, so that's there, times t, plus 1/2 times ay, -9.8, times t squared. All right, well, let's continue on from there. I've got 1, 2 equations and 1, 2 unknowns. The x equation, the y equation, v naught, and t. So 2 equations, 2 unknowns, you know how to solve that. Let's solve this for v naught. Move this around. We're solving this equation for v naught. Gets us, when you divide 0.819 through on both sides and divide t through on both sides, you get that v naught is equal to 17.09 over t. I can take that v naught there, this, plug that in right there for that v naught, and I get that -9 is equal to 0.574 times v naught times t minus 1/2 times -9.8 times t squared. Those t's cancel out, and I do the math, and I take that, put it over there. -18.8 is equal to -4.9 t squared. Solve for t. T is 1.96 seconds. And then what can I do with this t? Well, I can plug that in right there and use that to solve for v naught. So I plug in that time, 1.96 seconds in there. V naught, 0.819 is equal to 14. And then I can solve for v naught. V naught, 8.72 meters per second. That means that when the skier was right there, he was going at 8.72 meters per second in that direction. We got it. We got that part, at least. Now, let's use energy to figure out the rest of it. How do we figure out the height to start this whole adventure? Well, as I said, we need energy. What's the energy equation? Delta E is equal to W. Is there any outside work? Well, I never mentioned friction, so I'm going to guess that there's no outside work going on here. So therefore, delta E is equal to 0, and therefore, energy initial is equal to energy final. Remember all that stuff? Remember doing that stuff? Well, maybe only 100,000 years ago? Yeah, that's also important stuff that we need to put back into our brains. What kinds of energy did the skier have initially? I said that the skier starts at 0 initial speed, so no kinetic. Does the skier have any spring energy? Nope. Rotational energy? Nope. Gravitational potential energy, yeah. Skier starts with some gravitational potential energy. What does the skier end up with there? Well, it's actually probably a good idea to figure out where we're going to set h equal to 0. I'm just going to set h equal to 0 to be just there at the bottom of all this. That's fine. H equals 0 can be down there. We're looking for this anyway. So let's just use there as 0. And so what kind of energy does the skier have right there? Gravitational potential for being off the ground, off of h equals 0 at least, and kinetic, because as we found out in the last part, he's going at 8.72 meters per second. So we need gravitational potential and kinetic at this point. And so we get it. This is going to help us figure out what we're solving for. H start, that height. That is going to be from the 9 meters high that he is at that point. And that is going to be from the 8.72 meters per second that he's got leaving the ramp. Now, remember, these were the initial conditions of the previous part. We had the final condition, the end of the problem over there, and the beginning of the previous part of this on the last sheet of paper. We were solving for what was going on in the beginning, the initial velocity. That initial velocity in the first part is the final velocity of the second part. Now, this can get confusing to some people. So it's almost like watching it back in time in a way, and that works in physics. So get some practice with that. Let's plug in equations for these. And if we do that, we get the mass times acceleration due to gravity times the starting height, whatever that is equal to the mass times the gravity times the height of the ramp, 9 meters, plus 1/2 times the mass times the initial velocity squared. The initial velocity, or sorry, that's the final velocity. See, I'm messing that up too. That's the final velocity. That's the 8.72 meters per second from the previous part. What can we cancel out? Masses, get rid of those masses. Okay, plug in other things that we know, and we've got g times h, g is 9.8, times h is equal to 9.8 times 9, that 9 is the height of the ramp, the height, 9 meters. Notice that it's positive 9, because we're measuring it as how high you are from h equals 0. Plus 1/2 times the final velocity of this part of the problem, which is the initial velocity of the first half of this problem. And you can solve for h start, and that ends up being 12.88 meters. So if you're going if you wanted to land 14 meters away from this 9-meter ramp, and the ramp had an angle of 35 degrees, you'd have to start 12.88 meters above this particular h equals 0, above the point where you're landing, I guess. That is how you do this problem in reverse, in effect. We started all the way back here. We started knowing how everything would end up. We started knowing the exact end of the question. We knew that the skier would land 14 meters away from the end of the ramp. We had to go from there to figure out, okay, how fast was he going right there? And then we used that to figure out, okay, where did he have to start in order to be going that fast right there in order to land right there? This is taking a problem and going backwards through it, figuring out what you need in order to get what you want to get. This is a much more of an engineering kind of problem. Your customers will come to you saying, I want this. I want to land 14 meters away from the ramp. You have to get me there. You have to explain to me how to get to do what I want to do, and I'll pay you $100 million to do it, whatever. I don't know how jobs work. So you have to figure out, okay, the customer wants to do this. I've got to figure out how to make that a reality. So if the customer wants that, I know that, well, maybe I can figure out how fast the customer has to be going when they're right there. And then I can backtrack even farther to figure out where to begin everything. This is very much more like how engineering things work. Having a goal and figuring out what you need to do to get that goal. And that's a good lesson for everything. So as you're studying for the final, make a goal, and figure out how am I going to get to that goal. Hint, the answer is studying, but I'm confident that you will be able to do that in any case.